cosine theta is equal to u dot v divided by length of u, length of v. Alright? So in order to find the angle between two given vectors, I compute the dot product. I compute the length of each one of them, and then I use this expression. Alright? If you're getting a very special value, like square root of 3 divided by 2, or 1 over 2, or 1, or 0, then you'll be able to find what this angle is explicitly, right? If not, the only thing you need to do is just write theta to be r cosine of whatever value we have over here. Right? That's what we did. And if I want to find a vector which is orthogonal to both of u and v, what do I do? I think I have Muhammad over there. Cross product of u and v. In fact, I can even do v and u. So these two are both orthogonal to v. Are orthogonal to u and v. And we also talk about how to normalize these vectors to make it a unitless, right? So that's going to be how do you normalize this? Which means if I want to find a unit vector, which are orthogonal to both u and v, what do I do? Remember that? Divide by length. Okay. This is a pretty universal method to normalize a vector. No matter what vector you have, as long as you want to make it unitless, you just divide by its length. Example, right? U or v. Okay. So that's pretty much all we learned from this class. So the other thing I want to talk about is when you write down the vectors, use these arrows. Use these arrows to indicate this is a vector value function or vector value quantity. Right? In a book or in the quizzes or tests or final, you might use the bold letter to indicate the vectors. But always use arrows if you want to indicate the vector. As I said in Monday's class, one of the most important steps in the whole semester is to identify the problem. And where you're dealing with numbers, where you're dealing with vectors. Always use these arrows, you will keep yourself checked. Okay? I am doing the vector computation, so I have to be careful if I'm dealing with a two-dimensional vector. That means I have x and y components to worry about. If I'm dealing with a three-dimensional vector, I have x, y, z components to worry about. Okay, so use these arrows. Questions? Yeah.
So when you're solving for dot product, it's usually a number, right?
It's not usually, it is always a number.
Okay. And then cross product is usually
It's always a vector. Okay, so next I want to quickly go to 12.5, lines and curves. In R2 or R3. Okay? In fact, lines are special cases of curves. Right? So if you have a straight curve, don't change it at all. You're dealing with a line. I want you to have this in mind. So if I have a curve in the two-dimensional plane, this line is actually corresponding to a vector value function according to the following rule. For any given point on the curve, I can line together this point with the origin, and this will give me a vector. Alright? So any line on the curve will uniquely determine a vector coming from the origin to this point on the curve. As this point is moving, this vector is also changing. Alright? So have this dynamics in your mind. What we're doing with calculus is essentially dealing with dynamics. We're studying how things are changing. Right? So you have to have this dynamics in mind. So this curve is given, then there's a unique vector value function determined by this correspondence. Or going the other way around, if I have a vector value function, and because this is something that is changing, so if I have a vector, but this vector is changing according to time, so I can find a point given by this vector for a fixed time. As this time is changing, I will have a curve going, right? So this is going both ways. If you have a curve, there's a vector value function. if there's a vector value function, you can try to find the points going by the time. So that will give you a curve. So this one as a vector value function will determine a curve. I will give you the simplest example. So if I say R of t is equal to cosine t sine t. So here we're essentially saying x is equal to cosine t, y is equal to sine t. Right? The x component is taken from cosine t, and y is taken from sine t. Have you seen this kind of curve before? You definitely have seen this before. Maybe you didn't realize, but this is just a unit circle. This is just a unit circle. Okay. One way to be convinced this is a unit circle is I already said x is equal to cosine t, y is equal to sine t. We can use a trigonometric identity to eliminate to get an equation involving only x and y. And that trigonometric identity is actually our favorite. What trigonometric identity have you learned before? Which is sticking in your mind forever. Sine squared plus cosine squared is equal to 1. So this is essentially x component, this is y component. If I want to eliminate t, I just square both and add them together. I'm getting x squared plus y squared is equal to cosine squared t plus sine squared t, which is just equal to 1. And you definitely have seen this equation before, right? So x squared plus y squared equals 1 is going to determine unit circle, all right? Okay, so still I want you to be able to go both ways. In one direction, I should be able to eliminate the variable t to get an equation involving x and y. And I can use my previous knowledge that this equation is an equation of a unit circle. On the other hand, if I give you this equation, x squared plus y squared is equal to 1, I want you to be able to translate this into a parametric equation in terms of introducing a new variable and write down two equations to determine x and y separately. Are you with me? Okay? So we have done one direction. I have these parametric equations. By parametric equation, you have a separate parameter t to determine x and y. All right? If I have these two parametric equations, I will be able to eliminate this parameter t to get this equation x squared plus y squared is equal to 1, which is telling me this is a unit circle. On the other direction, if I'm giving you this equation, you should be able to translate this back into a parametric equation. Okay, so throughout this semester, we're going to use this a lot. We're going to use this a lot for some special curves, especially circles, right? So if I want you to write down the circle equation, you should be able to write down x squared plus y squared is equal to 1 if the radius is 1 and the center is 0. And also, I want you to be able to write down this equation as well. Okay, so parametric equation. So this is extremely important. We're going to use this in our following chapters. So if I ask you what is the equation for a circle, before this class you probably know x squared plus y squared is equal to 1. But also I want you to be able to recognize this is also defining a circle. Are you with me? This one is also defining a circle. Remember this guy. And more generally, if I have a vector value function which is given by a cosine t, b sine t, two different values of a and b. What is his curve and how do I convince myself it is the curve I'm thinking of? Just comparing these two. Okay. In order to see what his curve is, I might want to eliminate the parameter t. So according to what we did here, how can we eliminate? Think about it. I still want to use cosine squared plus sine squared is equal to 1. And I know this guy is equal to x. This guy is equal to y. So how do I get cosine? How do I get sine?
A over x squared b over y squared equals 1?
Yeah, that's correct, but more probably more frequently will be how about I divide x by a, I'm getting exactly cosine, right? I divide y by b, I'm exactly getting a sine, right? So I square both, and I add them together. This is going to give me a 1 in the end. And you have seen this equation before. That is a, what is it? Not really, no. This is an ellipse line. So with x-axis a and y-axis b. So this length is a and minus a. This is b and minus b. Okay, so this will be the equation of an ellipse, and the parametric equation will plus a cosine t and b sine t. Okay. Again, I want you to be able to recognize the same curve by two different equations. One containing parameter, the other one is the equation involving x and y. Any questions? Okay, so next I have a couple of remarks to make. First one, so there are two representations. Okay, so one is xy, the other one is with a parameter. I want you to be able to go both ways. Second one is I can also indicate the interval of the parameter t. So interval, or maybe more strictly speaking, let's just talk about the domain of t. I didn't say anything about the domain of t or the range or what values I can put for t. For instance, here, if I go t from 0 to 2 pi, okay, for 0 to 2 pi, for any given t between these two values, 0 and 2 pi, plug in these parametric equations, I will be able to find a point on my curve. All right? For instance, if I let t equals 0, I'm at cosine 0 equals 1, sine 0 equals 0, so I'm at this point. All right? So if I let t equals 2 pi, I'm getting cosine 2 pi equals 1, sine 2 pi equals 0 as well, so I'm at this point as well. All right? Any point of t between 0 and 2 pi, I'm actually on the curve. For instance, if I let t equals, let's say, pi half, what do I have? So cosine equals 0, and sine equals 1. So I'm actually at this point. So this is t equals 0. This is t equals pi over 2. And in fact, you can easily check this point is corresponding to t equals pi, and this guy is t equals 3 pi over 2. So if I have this domain of t, I will be able to get a whole unit circle. Am I right? Because I go from this point, as t is increasing, I go this counterclockwise way, and then I arrive at the beginning point in the end. Okay? So I want you to ask yourself this question. What if I want to have the upper unit circle? What if I want to have the equation for the upper unit circle? I don't need to change this parametric equation, right? It's still on the circle, so these ones are still okay. However, because I only want to have this half of the circle, I want to change my domain of the parameter. Instead of going all the way from 0 to 2 pi, I only need a 0 to pi. Okay? So the same equation, but t is going from 0 to pi. How about I want the right half circle? How about I want to use this half for my curve? You have a lot of freedom to choose your parameter t, right? Because these cosine sine functions are periodic functions. There are a lot of freedom to choose. You can do from 0 to pi half, and then from 3 pi to 2 pi. But if you only have one domain for your parameter t, you can just go from minus pi half to pi half, right? This one will give you a whole right unit circle. So pi half is less than t, so this one is pi over 2. Okay? You can ask a whole bunch of questions, similar questions, even for this ellipse as well. How about I want to have the upper half or right half same parametric equation, but you need to change the domain of the parameter. Okay? And the very last remark I want to make is the orientation. By orientation, I mean on this curve, when my parameter t is increasing, there is a particular direction for the point to move around. For instance, I'm still staring at this unit circle. I have this unit circle defined by this xy equation. I don't have any orientation at all. Right? In order to check the point is on the circle, according to this equation, the only thing you can do is to plug in numbers and see whether it is satisfying this equation or not. However, if I'm going through this equation, the parametric equations, there's a particular direction. As t is increasing from 0 to 2 pi, the points are moving in this direction, right? And this is going to be the orientation of the circle, which is saying if your parameter is increasing, no matter what domain you have, you can have domain